For the reactor used in the steam methane reforming, the PBR reactor is used in the SMR reaction because the steam methane reforming method requires a catalyst to improve the reaction. So, packed bioreactors are frequently utilized for this process. Aside from that, because this project wants to produce a significant volume of hydrogen, the PBR reactor is a better choice than the others because it has the advantage of forming products in large amount due to higher contact between the reactant and the catalyst. Furthermore, PBR will have no trouble dealing with processes that requires high operating temperatures and pressure, making it ideal for the SMR reactor, which requires temperature range between 700 degrees Celsius to 1000 degrees Celsius, and a pressure range of 300 kPa to 2500 kPa. As for catalysts used in this process, there are many active metals used to promote the SMR process, but nickel is the most abundantly used metal because of its high reactivity and low attrition during set-off experiments. Nickel is expensive compared to few other available options such as manganese, ferrum, and copper, but this is compensated by using a lower percentage of nickel in the catalyst. And nickel-based catalyst can withstand a very high temperature, which is between 900 degrees Celsius to 1100 degrees Celsius, and nickel exhibits a good mechanical strength. And the use of alumina-based supporting material has been investigated extensively in literature. It has been found that aluminum oxide showed a good reactivity and no agglomeration. And depending upon the feed used, different metals and supports are used for steam reforming process. Moving on to the next chapter, which is steam methane reforming process, there are 4 significant steps, which the first one is steam production, and then moving on to reforming reaction, and then we have water gas shift reactor, which is WGS reactor, and the last one is gas purification, which is the separation. First step, which is steam production, water must be in the form of steam at a very high temperature in order for the reaction to take place, and water enters the furnace as a liquid and is heated to temperature upwards of 1273 Kelvin, and this high temperature fosters reaction between methane and water to capture as much hydrogen as possible from the process. For the second step, which is reforming reaction, steam from the furnace is mixed with natural gas, which contains methane, to start the reaction, and the steam gas mixtures enters the reformer from the inlet manifold. The reforming tubes are surrounded by burners, keeping the temperature of the mixture above 1500 Fahrenheit, and at this temperature, methane reacts with steam to produce hydrogen and carbon monoxide. The presence of nickel catalyst helps this process to react more quickly and to retain more hydrogen gas. The hydrogen-carbon monoxide mixture exits the reformer via the coal outlet manifold, so carbon monoxide is not a useful product of the reaction and may be harmful if released into the environment. And for the third step, we have water gas shift reactor. And to consume carbon monoxide and producing more hydrogen, carbon monoxide from the reforming reaction enters the water gas shift reactor. And this reactor is filled with water and an iron chrome-based catalyst, which causes steam to break down into oxygen and hydrogen. Hydrogen is captured while oxygen joins the carbon monoxide from the reforming reaction to produce carbon dioxide. And the last step is gas purification, which is for separation. The gas mixture exiting the WGS reactor is not pure hydrogen and needs to be further refined to meet the customer's specifications. There are many ways to purify hydrogen, but pressure swing adsorption is the most common in an industrial setting. So the gas mixture enters the purifier where specific adsorptive materials traps contaminants at high pressures. So purified hydrogen is pumped out of the vessel, and finally the vessel is depressurized to release trapped contaminants. PSA is used for the removal of carbon dioxide, methane, carbon monoxide, and water from hydrogen. And in order to maximize the selectivity and percentage yield of hydrogen, first we can increase the concentration of methane. By increasing the concentration of methane can greatly increases the number of moles of hydrogen by 3 times, and also by Le Chatelier's principle, we can predict that the amount of methanol will increase, thereby decreasing the total change in carbon monoxide. Other than that, we can also increase the inlet temperature, which is the reaction temperature when the pressure is constant. Because the overall heat of reaction in this pipette reactor is endothermic, this shows that the whole process absorbs more energy in overall. So according to the principle of the Le Chatelier's, endothermic reaction favors a high temperature condition.
My name is Nur Irdina Ishaq. I will explain about process modeling and simulation part on the topic assumption, online simulation, and deviation error. And it will be continued for the next part by Firdaus Zahrin. To run the simulation, it is important to determine the parameter first. All the assumption is stated below because the assumption will affect the whole simulation results. Wrong assumption give a wrong results as the simulation calculate based on the data that has been set up by the observer. This is the condition that is needed for the feed stream for natural gas and steam given the ratio by 1:3. Thus, we assume that the mole flow of steam and natural gas by 2000 kmol per hour over 6000 kmol per hour. Then, all the assumptions for both reactors are from reference with a range of operating pressure and temperature. Based on the PFD shown, firstly, mix the feed streams into one stream. These fluids are mixed perfectly in mixer with a condition that suits the reference temperature and pressure for SMR reactor inlet. Then, the fluid is flowed to the compressor to increase the fluid pressure. We use the compressor because the fluid is in gas phase. Then, to match with the optimum temperature for inlet water gas shifting reactor that based on reference, the fluid is flowed to the cooler. It is to lower the temperature of the fluid as the fluid that comes out from the SMR reactor has high temperature that exceed the operating temperature for WGS reactor. After running the simulation, the outlet mole flow and mole fraction for each component for each reactor is given below. In this part, we need to validate the value by comparing the results from simulation and reaction engineering calculation. Thus, the deviation error can be calculated based on the formula given. The deviation error for each mole flow of the components for each reactor is calculated. The deviation error results for each component mole flow for the SMR outlet and WGS outlet is listed below. The error might be due to the conversion value. As in reaction engineering part, they need to calculate it for the conversion value. However, for the simulation part, there is no value assumed or shown in the PFD. The error also might due to the assumption made by process modeling simulation part but does not take into consideration by reaction engineering part, which affects some of the calculation that gives the error value.
Hello, my name is Muhammad Firdaus bin Zahari and now I will explain about topic 4, sensitivity analysis. For the first one is the effect of pressure on reactor performance. So for the range of the pressure is from 1000 kilopascal to 5000 kilopascal and the step size is 400 kilopascal. The independent variable is the pressure of natural gas stream and dependent variables are mole fraction of all components at WGS outlet, mass fraction of hydrogen at WGS outlet, mole flow rate of hydrogen at WH outlet, mass flow rate of hydrogen at WGS outlet, and energy consumed by the WGS reactor. Based on the results, when the pressure increases from 1000 kilopascal to 5000 kilopascal, the mole fraction of hydrogen at WGS outlet also increases from 0.221019 to 0.221074. The increase of pressure at natural gas also increases the mass fraction, mass flow rate, mole flow rate of hydrogen of WGS outlet stream. The system will adjust itself to the new conditions when the pressure is applied to the system. The pressure increase will cause the molecules of component to pack with each other, and this causes the rise in temperature of the system. The packed molecules contain more molecules per cubic centimeter of the space available between the molecules. This results in more molecules to hit each other and hit the wall in higher frequency compared to when the pressure is lower. Although the pressure of the natural gas stream increases, but the energy consumed by the WGS reactor can be seen constant at 5.66 to the power of 7 watt. This shows that even though the quantity of product increases when the pressure is increased, the energy consumed by the WGS reactor remains constant. The mole fraction of methane and water also be seen decreasing as the pressure of natural steam stream increase. So for the second one is the effect of temperature on reactor performance. The range of the temperature is from 1000 degrees Celsius to 1500 degrees Celsius. The step size is 50 degrees Celsius and the independent variable is temperature of natural gas stream in degrees Celsius. The dependent variables are the same as the pressure one. So based on this graph, when the temperature of natural gas stream increases from 1000 degrees Celsius to 1500 degrees Celsius, the mole fraction of hydrogen at WGS outlet increases from 0.2210 to 0.3208. This indicates that as the temperature of natural gas increases, the mole fraction, mass fraction, molar flow rate, and mass flow rate of hydrogen at WGS stream outlet also increases. The mole fraction of methane and water can be seen decreasing as the temperature increases. This is because the temperature of the system will affect the kinetics of the molecules that leads to the collision of the molecules. First is collision frequency model. As the temperature increases, the collisional frequency of the molecules also increases. From the equation above, the collisional frequency ZAB is directly proportional to the temperature. So when the temperature increases, the collisional frequency of the molecules will also increase. Then the reaction occur inside the reactor will also increase and the molecules are moving with higher velocities. This also can be seen in the Amanton's law, where the law stated that increasing in gas temperature also causes the pressure of gas to increase as the volume is constant. The pressure increase will cause more frequency collision between the molecules, thus increases the rate of reaction and product produced by the system. So the third one is the effect of flow rate on reactor performance. For the range of the flow rate is from 2000 kmol per hour to 3000 kmol per hour. The step size is 100 kmol per hour and the independent variable is the flow rate of the natural gas stream. The dependent variables are the same as the pressure and the temperature. From the results obtained, we can see that when the mole flow rate of natural gas stream increases from 2000 kmol per hour to 3000 kmol per hour, the molar flow rate of hydrogen also increases from 2056.277 kmol per hour to 2466.078 kmol per hour. The mole fraction, mass fraction of hydrogen also increases as the molar flow rate of hydrogen increases. This can be further explained when the mole flow rate of the natural gas stream increases. The mole fraction of methane also increases as there is only methane in natural gas stream. The relationship is as the equation below. Molar flow rate equal to mole of component over time. According to Le Chatelier's principle, the position of equilibrium will move in a way opposite to the changes that was made to the system. The increase in the pressure will cause the position of equilibrium to move to the right side, which is the reactant. This is why the value of mole fraction and molar flow rate of methane and hydrogen increases as the molar flow rate of natural gas stream increases. So for the last one of the analysis is the effect of composition on reactor performance. The range is 0.1 to 1.0 and the step size is 0.1. And the independent variable is the mole fraction of methane in natural gas stream. The dependent variables are the same across the four effects. From the results obtained, when the mole fraction of methane in natural gas stream increases from 0.1 to 1.0, the mole fraction of hydrogen that was produced at WGS stream outlet increased from 0.125908 to 0.221005, along with the mass flow rate, mass fraction, molar flow rate of hydrogen. This once again can be explained by Le Chatelier's principle.
Hi, my name is Nobatusha Akila binti Arman and we shall continue with CEB 2063 separation process 2 explanation. Well, before we move to the H2 enrichment unit, there is another unit particularly placed right before the H2 enrichment unit that we should focus on as well, which is called carbon dioxide CO2 removal unit. This unit helps to capture the carbon dioxide produced from the combustions from the reactions before the stream is then releases to the hydrogen enrichment unit for further enrichment. Approximately around 60% of carbon dioxide is produced in a steam reforming hydrogen production plant fed by natural gases. There are various technologies available for carbon dioxide capture, for example, adsorption technologies, membranes technologies, cryogenic processes, or even various combinations of these technologies. But according to the recent study by Government 2013 quotes that one of the current best available carbon dioxide capture technology is amine-based absorption and PSA systems. While the technology is decided based on the desired purity of carbon dioxide or how much carbon dioxide needed to be captured alongside with consideration of the cost of building up the plants. Moving on to the calculation part of this absorption tower, the efficiency assumed is 90%. Products to be absorbed is carbon dioxide. Percentage of the carbon dioxide inlet is 1.04 mole % coming from the CEB 2053, and also some other assumptions made as you can see on the slides. First one, we calculate the molar flow rate and mole fraction on each outlet using general mass balances and material balances. At G1, the inlet flowing at 1850 kilomole per hour, while at L1 that consists only pure amine as the solvent flowing at 2000 kilomole per hour. All the calculations made are recorded in a table as you can see and on the slides. We then calculate the number of stages in the adsorption tower by using the Cramley's equation. Aside from using Cramley's equation, the calculation can also be done by using graphical method.
Hi, my name is Muhammad Azhar and I'm going to present about hydrogen gas arrangement unit. So the reason why hydrogen gas arrangement unit are very important in our separator system is because one is to remove impurities from hydrogen gas via adsorption. Two, since its presence of CO2 can be negligible, methane will be our target impurities, so the absorption will be used in order to remove these impurities, which is methane gas. The third one, which is this impurity system, will be arranged in a series of 4 absorption beds by 2 cycles, which means the first 2 will be arranged as 1 cycle, and then the second 2 and the third and the fourth absorption bed will be arranged in another cycle. This is to ensure that the absorption process of the methane will be as efficient as possible and to ensure a very high purity yield of the hydrogen gas. In our H2 enrichment unit, we were gonna use pressure swing absorption. The reason why we use pressure swing absorption is it can yield up to 99.99% H2 gas. It has high H2 recovery rate, which is around 60 to 70%, and it can handle to a very tremendous amount of volumetric flow rate. In our absorption system, the absorbent used in our enrichment unit will be Zeolite 13X. The reason why we use Zeolite 13X is because it has high absorption capacity, it has high absorbent recovery rate, and it is suitable for the absorption of methane. And Zeolite 13X is commonly used in our industrial process. These are the specifications of our H2 enrichment unit. Noted that the bulk part of the specification is actually used as a calculation, will be needed as a part of a calculation, while the non-bulk part from the specification table are used based on literary material, the type of absorber, bed length, wall thickness. The type of absorber are determined to be will be using PSA unit. The bed length is determined to be 0.82 meter. The bed volume will be 0.42 times 10 negative 3 meter cube. The bed diameter will be 2.32 times 10 negative 2 meter. The bed porosity will be 0.41. The wall thickness is 4.1 times 10 negative 3 meter. The column material will be determined to be stainless steel and is a resistant corrosion and also resistant to have high specific capacity. The absorbent will be Zeolite 13X as determined by our as been explained by earlier. Absorbent diameter is determined to be 77.95 times 10 negative 3 meter as been calculated. The absorbent volume is determined to be 0.248 times 10 negative 3 meter cube. The theoretical maximum absorption capacity is 51.546 mg per gram. Feed temperature is 75.5 degrees Celsius and the MTZ being determined is 0.2343. And lastly, this is the calculation that have been done in order to obtain the value of the property in the bulk part of our specification table.
I will be the representative to describe our group's reflection according to the Gibbs reflective cycle. We firstly divided the tasks among us via an online meeting once the question of the integrated design project was released. This is to ensure that equal distribution of tasks are made and everyone is clear with their responsibility and part. Throughout the whole designing project, our group members agreed that we had a good communication with one another by utilizing the WhatsApp group function. Whenever there is a problem, we will be communicating through it. While our group members are very helpful and responsive, it was a very good teamwork for everyone. The project went very well since all of us contributed and played our role create our role very well. Some confusion that required us to reevaluate our design happened, but we managed to pull through from a thorough discussion we had. From this integrated design project, our group agreed that we learned a lot of new knowledge and experience. For example, it's always okay to make mistakes for as long as we are willing to learn from it. Another one would be, it is terribly important to play our individual roles in a group project, as it will help not only ourselves but our members too. In the future, if we were to work together again, it will be best to start working just a little bit earlier. This is all from us. Thank you.